Okay, everyone, grab a tasty beverage because this is going to be a good one. I'm going to attempt to debunk the debunker, notably that Joe Rogan podcast 2141 with Bart Sibrel. Is it Sibrel or Sibrel? I'm not sure. But he's the gentleman who claims that we did not go to the moon and that he can prove it. So, without sort of saying, hey, I solidly believe we did go to the moon or we didn't go to the moon, that's not really the point of what I'm going to say. What I'm going to do is debunk his argument because I feel like his scientific procedure or lack thereof, or his sort of narrative logic or lack thereof, is faulty. And so that's the first point. And then the second thing is I will clarify a gross, meaning big, not disgusting, but a gross error that Bart makes. And by showing me he doesn't understand this key scientific fact or set of facts, it kind of just cancels out all of his so-called research for me, because this is essential to his argument of why we didn't go to the moon. Okay, so let's start with his sort of logical process or lack thereof. Now, throughout the entire podcast, Joe Rogan gives him the room to present his argument, and then Joe Rogan says, hey, I'm going to steel man this, meaning Joe Rogan's going to play devil's advocate, which is only meant to help Bart provide the counter argument to Joe's counter argument to kind of strengthen what Bart's trying to say. And more than once, Bart just gets kind of refuses to do that, or says, no, we don't need to. And Joe pushes back a little bit and says, well, yeah, we do. We need to, you need to play this out with me. And it's kind of like, Bart, Joe has the biggest reach there is. He's trying to help you, and you're getting an attitude with him about providing these counter arguments. So it's like, why did you even come on the podcast if you're not going to play ball with Joe Rogan? And he's not doing this in a mean or nasty way. He's literally trying to help Bart build his argument. But nevertheless, that's Bart's approach, is no, we don't have to do this. Okay, so now the second big fault I find with Bart trying to build his argument is that his points of reference are just himself. He's completely circular because he keeps directing Joe or the audience, just go to my website and you can see this video. Well, it's a video that you've produced. Sounds like you've found this female with a British accent, or I don't know if it's AI programmed to be a female with a British accent, so it sounds very, very knowledgeable because it's got a British accent. But you have to direct people to primary resources if you are building a solid argument. So, for example, I'm not going to tell anybody who listens to my videos, hey, don't go watch the fight for yourself. Only listen to my video because my video is the truth. No, I'm not. That's ridiculous. I'd tell you, watch the fight itself before you even listen to what I have to say. Enjoy the fight for yourself. Form your own opinions about it. And then if you're curious what my take was, then yeah, come listen to what I had to say, and let me know what you thought in the comments. That's kind of the whole purpose of me making these videos. But I certainly would never tell someone, no, you must not go to watch the actual fight for yourself. That's forbidden. Okay, but that seems to be Bart's take on how he's going to provide evidence. Okay, so now I could tediously sort of try to shoot holes in every single scientific assertion that Bart makes, but I just don't have the stomach for that, and that's not really gonna cut to the chase. So I'm gonna hone in on just one, and this happens at about 29 minutes in, where Bart confuses or conflates or puts these two concepts together. He confuses X-ray radiation with cosmic radiation. Now he's trying to cite the fact that we need a 1/4 inch of a lead blanket when we get X-rayed to protect the parts of our body that aren't being X-rayed from this dangerous X-ray radiation. It's true. That's why the X-ray technician's in another room and the door is shut, and then they hit the button to shoot the X-rays through you so they can get the image. It is dangerous, but X-rays are a completely different form of radiation than this cosmic radiation. Now, one of Bart's main arguments for proof that we never went to the moon is that there's so much cosmic radiation that it would kill an astronaut. Okay, I'm going to debunk that for you a little bit further down the road, but the fact that in the same sentence he's basically saying, well, hey, if we need a 1/4 inch of lead for this millisecond of X-ray, then there's no way we could survive cosmic radiation. But they're two completely different forms of radiation. Now, in a second point during the podcast, and I apologize, I can't timestamp this for you, and I do not feel like listening to this whole thing like for a third time, because trust me, this is for me like listening to the fingernails on the scratching on a chalkboard, or it's also like kind of listening to people tell me that Tyson Fury had an egg weight in his glove when he fought Deontay Wilder. Like, there's only so much of this I can stand. So forgive me, I don't have the timestamp for Joe Rogan's error, but Joe Rogan also confuses these two things. Because he refers to cosmic background microwave radiation, acronym CMBR. And he also confuses that with cosmic radiation. Now, I'll forgive Joe Rogan that. I'll afford him grace on that, because he's a layman, number one. This is not, he hasn't devoted his life to this. And number two, cosmic microwave background radiation has the same two words, right? Cosmic and radiation. So it's easy to think that they're the same thing it's easy to think that that's just another form of cosmic radiation. And I will admit that it wasn't until I did graduate studies in space studies that I was forced to distinguish between, say, dangerous microwave or X-ray radiation versus cosmic radiation. They are two completely different types of radiation. So microwaves and X-rays and the visible light, the light that allows you to see this right now, the light from the sun, these are all forms of what we call electromagnetic radiation. And each of these forms of radiation, a lot of physicists and scientists just call it light, just because light is got one syllable and radiation has three, so it's easier to just call all of this light. But when we use that word light, we're referring to electromagnetic radiation and visible light, microwaves, X-rays. These all form what we call the electromagnetic spectrum. Okay, so now I gotta give you a little bit of a science lesson. So all of these forms of radiation, or light, if you will, have different frequencies. Frequency means how fast or how many times something vibrates back and forth in 1 second. So frequency is measured in hertz, Hertz. And so, for example, your computer has a speed of whatever, one something gigahertz or whatever it is. So that means it's vibrating, it's doing those computations that many times in 1 second, which is pretty amazing. Those of you who play music know that tuning fork, we usually tune to 440 hertz, right? So you get the idea. Now, every form of electromagnetic radiation has a different frequency or a different range of frequencies, and simply by the nature of it being a wave, it also has a wavelength. So the higher the frequency of the radiation, the lower the wavelength. Okay, so let's just look at the visible light we can see. We see Roy G. Biv, as we call it: red, orange, yellow, green, blue, indigo, and violet. Red has the lowest frequency, so it has the highest or biggest wavelength. Violet has the highest frequency, so it has the smallest wavelength. Okay, now, what you should know is this amount of light that we can see as human beings forms an incredibly small sliver of the entire electromagnetic spectrum. Now, let's just go just outside what we can see. So, just beyond violet, there's, as you could guess, ultraviolet. We can't see that radiation, but insects can. On the other side of red, we have the infrared. Again, we can't see that, but a lot of nocturnal animals can, because they're basically looking for that heat signature, as we would call it, right? Infrared is present when heat is being emitted. Okay, now if we go even further out from violet, we're going to get to X-rays and gamma rays. So very high frequency, very small wavelength. So in that regard, yes, this sort of explains why X-rays are dangerous to us, and of course gamma rays are also, because they have high frequency. Now, for all of the electromagnetic spectrum, the higher the frequency, the more the energy that wave carries. So, while we can sit here underneath visible light and not get damaged, really, we cannot be subjected to X-rays or of course gamma rays, because they will damage us because they are carrying much more energy. I hope that makes sense. On the other side of red, we have the infrared, and then we have microwaves, and we have radio waves. Radio waves are what our cell phones use to receive the signal. It's not the wave coming out of, if you even have an analog radio. It's not that. Sound waves are mechanical waves. They're completely different from electromagnetic waves or electromagnetic radiation. Now, the other important fact about electromagnetic radiation is they all can travel at the speed of light, which is 3 times 10 to the 8th power meters per second. Also, electromagnetic radiation can pass through, lo and behold, outer space or emptiness. Electromagnetic radiation is, in fact, a form of a wave energy that does not require a medium. And by medium, I don't mean small, medium, large. I mean a substance to travel through, such as air. I mean, we look at air and think, oh, it's not visible, so there's nothing there. But there are, in fact, as you know, molecules of oxygen, or you and I would not be able to sit here and have a conversation, right? Water's a medium. Jello could be a medium. But electromagnetic radiation does not require a medium to travel. Now, let's take a look at, so the point here being, the electromagnetic radiation is dangerous if it's high frequency because it has more energy. There's a direct relationship. The formula, for those of you who care, E equals FH, energy equals frequency times Planck's constant. It's just a number. But, so in other words, you can see that as the frequency goes up on one side of the equal sign, the energy level is going to go up proportionally on the other side of the equal sign. All right, so now, what is cosmic radiation? And here's where both these guys messed up. Okay, cosmic radiation is completely different from electromagnetic radiation. electromagnetic radiation can be conceived of as wave energy and electromagnetic radiation. All these forms are carried by what we call photons, which are little particles of light, and they do not have any mass. That's critical. The cosmic radiation has mass. They have nothing to do with the electromagnetic spectrum. Cosmic radiation, and really I wish, maybe scientists should come up with another word, because I think radiation just creates too much confusion for people, evidently. But cosmic radiation are actually massive particles. These particles have mass, and they are ions. So if you can sort of remember some of your high school chemistry or middle school chemistry, I hope, to explain what an ion is and to explain just how big these particles are. So perhaps you remember that an atom, which is the smallest piece of any element, an atom is made of a nucleus surrounded by what we call an electron cloud. Now, inside the nucleus, we have the neutron. It's a particle that has no charge, and a proton, which is a particle with a positive charge. And the electron in the surrounding electron cloud has a negative charge. Now, the whole atom hangs together because the positive proton attracts the negative electron, and things are held together. There's also forces within the nucleus. I won't really get into that, but the point here is that I need you to understand that also the proton and the neutron are the particles that have the most of the mass. The vast majority of the mass of that atom is contained in those two subatomic particles. The electron, by comparison, has very little mass, and it's in fact, it exists in what we call a probability cloud. I don't want to get too deep in on this, but imagine a very large room, right? Imagine the space occupied by inside that very large room, and then imagine a golf ball. So that would be sort of the scale. It might even be smaller than a golf ball, but imagine that the golf ball is the nucleus, and that's where these neutrons and protons and most of the mass of the atom lie in this tiny little object. And the vast majority of the atom's space is just sort of emptiness, right? Occupied by this electrons that flit about outside the nucleus. Okay, so the nucleus contains the vast majority of the mass and takes up very little of the space. That electron cloud takes up the vast majority of the space, contains very little of the mass. All right, now let's jump over to our friend, the periodic table. And at the beginning of the universe, the Big Bang, took a while for even these subatomic particles to come into existence, but when they did, of course, the first atoms they formed were the simplest ones, which were hydrogen. So hydrogen has one proton, one electron, that's it. Now, remember, most of the times we want things in nature to be, as we say, neutral, right? So we want the same number of protons and the same number of electrons so that the atom has no charge. Okay, so now, what about, the protons, the number of protons in an atom is what gives the atom its identity. So, for example, you've heard that cliche of turning lead into gold. Well, if we wanted to be able to do that, we'd have to be able to go into the nucleus, change the number of protons in the nucleus in order to change the element lead into the element gold. And if we could do that, I think it would have been done a long time ago, right? But it's pretty much impossible to do that. We can't change the number of protons in an atom or in an element, because if we change the number of protons, the element's identity is completely different. Now, what about the neutrons? Well, in fact, we don't need to change the number of neutrons. Mother Nature does that. And so for each element, there are different variations of the element. Sometimes it will have one extra one or two extra neutrons, or maybe one less. Okay, so now the interesting things about these variations on the element, it's called an isotope, but the vast majority of them are radioactive, which means they just decay and go away kind of over time. Okay, so now we know we can't vary the number of protons. We know Mother Nature varies the number of neutrons. But what about these electrons that are sitting in this huge probability cloud way outside the nucleus and contain very little mass? Well, it's much easier to add or take away an electron because it's outside the nucleus, right? So this is how ions are formed. An ion is simply a neutral atom that has either gained or lost an electron. Now, if it gains an electron, remember the electron is negative, so now it has more negative charge on it. If it loses an electron, think about this. If someone forgives you your debt, it's almost like they gave you money, right? So when you lose an electron, when an atom loses an electron, it gets a positive charge, right? You lose your debt, the bank just says, hey, you're negative, but we're gonna forgive it. It's as if they gave you some money. So it's positive. Okay, so getting back to the cosmic radiation. Cosmic radiation are ions that are formed, yes, by our sun, but also some of them were formed way back, just after the Big Bang. They're formed by supernovas, when stars explode out there. A lot of this cosmic radiation is coming from beyond our solar system. So some of these cosmic radiation ions are small. They might be just the hydrogen or helium stripped of the electrons. So they have lower mass. Okay, but here's the problem. There are heavier cosmic ions, such as iron. Now, iron has 26 protons, and it could have a neutral iron atom has 26 electrons. So the maximum charge that could have is, if it loses all 26 electrons, it could have a positive 26 charge on it. Now all these cosmic ions are just floating around out there, out in space. And the problem is, not only do they have mass, unlike electromagnetic radiation, but these cosmic ions are also moving at the speed of light, 3 times 10 to the 8th power meters per second. So the formula for kinetic energy, the kinetic energy that this ion has is 1/2 times its mass times the velocity squared. So that's a pretty big number. This cosmic ion has a lot of energy, and traveling through space, if the astronaut is out there in space, now as this cosmic ion, whether it's simply the hydrogen, smallest one, or it's the large one, the iron ion, as these ions come through the spacecraft material, they want to steal electrons from the atoms in the spacecraft material, right? Because nature abhors a vacuum, as we say. So all these incoming cosmic ions want to become neutral. They want to steal electrons from, say, the spacecraft material. Okay, so let's say they do that. But the problem now is that sets off a type of chain reaction, because now the cosmic ions created a whole bunch of more additional ions by removing electrons from the spacecraft wall. So now we have these ions, and it's very similar to sort of a nuclear reaction, where just one particle can set off this chain reaction. Now, here's the additional problem, is that they'll penetrate the human body. They can penetrate our cells, and they will tear apart DNA. This is something that's mainly because of the cosmic radiation has mass. They act like a particle, whereas electromagnetic radiation acts like both a wave and a particle, but it doesn't have any mass. So you hear both Joe Rogan and Bart sort of get confused with this again, because they're saying, hey, well, you know what? Lead, like a lead blanket, protects us from X-rays. So I think Joe even asserts, well, we could make the spacecraft out of lead. Or, I've heard other people say that, and it's kind of a forgivable error, again, from somebody who's not coming from a scientific background. But here's the problem with building a spacecraft out of lead, because you think it's going to protect you from cosmic radiation. First of all, you'll never get it off the ground. It's going to be way too heavy. But second of all, if you build a spacecraft out of an element that's a large atom with a lot of protons, it makes the whole thing even worse in terms of dealing with cosmic radiation. It doesn't make it better. Here's why. Because you have this big ion coming in, say it's a charged iron ion, comes into hit the lead. Now lead's even heavier. It's got 82 protons. So now you're creating an even worse scenario, because you're going to create lead ions to rip through the astronaut's body. So again, we're confusing the fact that lead can protect us from X-rays versus lead protecting us from cosmic ions. The lead will just make it worse. So in fact, that's why in terms of spacecraft design, one proposal has been to use sort of the water tanks in the areas of the spacecraft that are going to be right adjacent to the astronaut, because water, being made out of hydrogen and oxygen, these are much smaller atoms, they'll create less massive ions. So it's really a question of minimizing the negative effect. We cannot just block out cosmic radiation. Now, you might ask yourself, well, so how come I'm sitting here and I'm not getting blasted with these cosmic ions? And here's the good news: neither you nor I are going to get hit with cosmic radiation. I'm assuming you're not going to go out into space. I'm not planning to either. Okay. Now, the reason we're protected here on planet Earth is because planet Earth is actually a giant bar magnet. You remember the bar magnets you played with when you were a kid. Now, if you did the thing with the iron filings around the bar magnet, you notice there are these little loops from one end of the bar magnet to the other. And that, in fact, is what's going on with planet Earth as well. I'll ask you to visualize an orange that you peeled. And if you hold the orange at either end, right, where all the sections are, those lines go from one end of your orange to the other end of your orange. Well, visualize those lines as being sort of the magnetic field of planet Earth. It's just a visual construct. There aren't actually lines going around planet Earth like that. But we have this magnetic field, and that, in fact, is what keeps us protected from these cosmic ions. So these cosmic ions that are hurtling through space and bump into our magnetic shield get neutralized, and in fact, that's what we call the northern lights. Nature puts on a beautiful show for us while protecting us at the same time. So while you're on planet Earth, you don't have to worry about cosmic radiation. Okay, so one of Bart's big arguments is we never went to the moon because astronauts would have died from the cosmic radiation. And he's almost right, because if we allow astronauts to stay out there indefinitely, yes, they're going to suffer from egregious amounts of damage to their DNA and to their bodies from this cosmic radiation. It's just completely unavoidable. So what does NASA do? They closely monitor how much time every astronaut gets to spend out there in space. With the understanding that, once you hit this threshold, sorry, you're done. We're just never sending you out there beyond the Earth's protective magnetic shield. We're not sending you out there anymore. So, of course, here's another counter argument to Bart, which is, he said, well, we never went to the moon because the astronauts would have been subjected to so much cosmic radiation that they would have died. All right, so these missions to the moon took about a week. There are astronauts that have been at the space station for over a year. It's not the distance that we're traveling that subjects you to more cosmic radiation. It's simply the duration of time that you're out there in space, because you can't predict where these cosmic ions are coming from or when they're going to hit. They're just all out there all the time. So it's time duration beyond Earth's magnetic field that's the determining factor for how much exposure an astronaut has. So, Bart's argument that the moon is further, therefore it's more dangerous, or that there will be more cosmic ion exposure because the moon is further from us, that just absolutely shows that he doesn't understand what cosmic radiation is. Now, just to circle back to that cosmic background microwave radiation, since I brought that up, and because Joe Rogan brought it up, that's a form of that electromagnetic spectrum, the microwave frequencies that were given off at the Big Bang. So they're still in existence out there, so to speak, and we quote unquote discovered them or encountered them I think it was in the late 60s or 70s when engineers and scientists set up these very, very large antenna, and they were constantly hearing this sort of interference noise and crackling, and they thought maybe there's something wrong with their antenna, or maybe they thought at one point that pigeons were messing around with it, but in fact they were picking up this microwave background radiation. I guess we just call it background because it's always going to be there, always has been there, but it's detectable. So again, that is just part of the electromagnetic spectrum. It's been there since forever, but it is not the cosmic ion that is incredibly dangerous to any organism, right? Not just human beings, any organism that we send beyond Earth's magnetic field. These ions can penetrate cells and therefore DNA. So incredibly damaging, and kind of sort of a reason I don't know about traveling to Mars, because that would be an even longer time duration, certainly, than even spending a year in the space station. So there's my little physics lesson for the day, to kind of hopefully clarify for you the difference between electromagnetic radiation versus cosmic radiation, and why you don't need to worry about cosmic radiation, but you should be concerned. You should know that there are risks for those higher frequency radiations like X-rays and gamma rays. Of course, the medical profession will protect you against overexposure to X-rays. So in any case, let me know what your guys' thoughts are. I'm not saying everything that Bart says is not true, but as a person devoted to science, it was very difficult for me to listen to the whole podcast and his pushback against Joe Rogan, who's really, I felt, just trying to help him present his counter arguments in a sort of coherent manner. But in any case, if you did listen to Bart, let me know what you think. If this little video helped you understand the difference between cosmic radiation and electromagnetic radiation, then I've done my job. Let me know what you guys think in the comments. Thanks for listening.